Imagine a situation where the fate of the world hangs in the balance. And despite having all the resources, you can't accomplish something as basic as connecting two parts. Sounds absurd, doesn't it? Perhaps you've encountered similar invisible obstacles in your own life, where a simple task suddenly became an insurmountable barrier. In this video, we'll uncover the secret of how one seemingly insignificant detail paralyzed an entire wartime industry, and how a brilliant solution was found. Forget everything you knew about mass production. The real problem wasn't a lack of workers or materials, but something far more fundamental. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, tell us in the comments where you're watching from. It's January 1942. At Boeing Plant 2 in Seattle, by all accounts, production should have been booming, churning out flying fortresses at a pace that could darken the skies over Germany. Instead, the factory floors resembled a colossal industrial gridlock. 63 B-17 bombers sat unfinished on the assembly line, each one symbolizing an unfulfilled promise that America couldn't keep. The U.S. Army Air Forces had ordered 3,615 of these formidable machines for delivery within the year. But by this point, Boeing had managed to deliver only 9. Just 9. That number sounded like a death knell. General Henry Hap Arnold, commander of the Army Air Forces, was not just disappointed. He was furious. In a heated meeting with Boeing executives on January 15th, Arnold stated unequivocally, without bombers, there would be no strategic bombing campaign. And without it, American soldiers would face years of fighting an entrenched Nazi war machine. The calculations were starkly simple and inherently terrifying. The problem wasn't a shortage of labor. In 6 months, Boeing had hired over 30,000 employees, many of whom were women who had never set foot in a factory before. Nor was there a deficit of materials. Aluminum from Alcoa arrived so quickly that it was barely used. The crisis was caused by something no one had foreseen. The bombers themselves were too complex for rapid production. Each B-17G consisted of 140,000 individual parts. The wings alone required 12,000 rivets on each side, joining 7 overlapping layers of aluminum skin to an internal framework designed to withstand up to 6 Gs during combat maneuvers. Traditional assembly methods, honed on smaller aircraft, simply couldn't cope with such complexity, collapsing under its weight. Philip Johnson, Boeing's production manager, walked the factory floor every morning at 5 a.m., clipboard in hand, witnessing the same nightmare scenario. At Wing Assembly Station 4, 17 workers crowded around a single wing section. They constantly got in each other's way. One riveter would finish a seam, step back, and immediately another needed access to the exact spot he'd just vacated. Then a third worker required that position for a different line of rivets. This choreography was sheer madness. Johnson timed it himself. 20 hours and 14 minutes were needed to complete a single wing assembly, from bare frame to the last rivet. 20 hours. The British were losing bombers over Germany faster than they could be built. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, tell us in the comments where you're watching from. Every unintercepted Luftwaffe fighter flying free due to the absence of American bombers in the sky meant more merchant ships sunk in the Atlantic, more factories operating at full capacity in the Ruhr, and more time for Nazi Germany to consolidate its power over Europe. Boeing engineers had already tried every conceivable approach. They redesigned tool access points. They created specialized jigs and fixtures. They even experimented with changing team sizes, believing fewer workers might reduce congestion. Nothing yielded results. The core problem remained unchanged. The rivet patterns specified in the engineering blueprints required work crews to sequentially occupy the same physical space in an overlapping order. Parallel work was impossible. You couldn't simply add more workers to speed up the process. This was a bottleneck embedded in the very DNA of the aircraft, and understanding it required delving into the tiniest details. By the end of January, Boeing executives were already having quiet conversations about the unthinkable, informing the Army that production targets couldn't be met. Some even whispered about bringing in Douglas or Consolidated to take over primary production. On January 28th, a secret memo circulated among senior management. Its subject read, Crisis Assessment, Viability of the B-17 Program. No one wanted to be the one who lost the war, because they couldn't figure out how to rivet aluminum fast enough. Walk onto Wing Assembly Station 4 any morning, and you'd see what superficially resembled organized chaos, but in reality was utterly disorganized. A wing section lay on a massive jig, a 32-foot skeleton of aluminum ribs and spars. 7 layers of aluminum sheet, each precisely cut and drilled with thousands of holes, awaited their turn to be joined in a strictly defined sequence. The process began at the wing root, where it would eventually attach to the fuselage and moved outward toward the tip. Sounds simple enough, doesn't it? But in reality, it was far from it. The engineering blueprint dictated that rivets be installed in rows running parallel to the wing's leading edge. First the first row, then the second, then the third, moving backward toward the trailing edge. This order made perfect structural sense. Each subsequent row reinforced the previous one, creating an overlapping shingle effect that evenly distributed the load across the wing's surface. Engineers at Boeing's Seattle Development Center meticulously calculated the position of each rivet to optimize the strength-to-weight ratio. On paper, it looked flawless. On the factory floor, it turned into a genuine catastrophe. Here's why. To install the first row, the riveter worked from the top surface, while the bucker, the person holding the bucking bar, worked from underneath, through the wing's internal structure. They required perfect synchronization. The riveter's pneumatic gun drove the rivet through pre-drilled holes with 3,000 pounds of force. The bucker's bar pressed against the rivet's tail from the opposite side, forming a mushroom-shaped head from the softened aluminum that clamped the sheets together. Miss the synchronization by even half a second, and you'd get a weakened rivet, which then had to be drilled out and replaced. Each such error added 3 minutes to the process. Multiply that by 12,000 rivets, and the errors became catastrophic in scale. But the real nightmare began when they started the second row. To access the second row of rivets, workers needed to position themselves exactly where the first row crew had just been working. Except the first row wasn't finished yet. Not completely. Quality inspectors had to check every 10th rivet with a borescope, a tedious process that took 15 minutes per wing section. So the second row crew waited and waited. Meanwhile, the third row crew, already prepared and ready to work, stood idle, losing precious time. The production schedule called for parallel workflows, but the physical reality of the wing's geometry made this absolutely impossible. Simply put, there wasn't enough space around the structure for enough workers to rivet multiple rows simultaneously. I think each of us has, at least once in our lives, faced a situation where it felt like the world had conspired against us personally. When everything goes wrong and you seem to be the only one who notices, that's exactly how the workers in the factory felt, where every day brought a new challenge. Have you ever encountered a problem that wasn't described in any instructions, but whose solution determined the success of the entire endeavor? In fact, I myself have found myself in a similar position more than once, when instructions proved powerless in the face of reality. But it is precisely then that truly groundbreaking ideas are born. And today we will delve into a story that proves that the most important decisions sometimes come from where they are least expected. In this video, we will unravel a mystery that allowed production to be accelerated many times over, in what seemed like a hopeless situation. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, don't forget to tell us in the comments where you're watching this video from. These rivet guns weren't just tools. They were industrial pneumatic hammers that shook your whole body with every shot. Compressed air hoses snaked across the factory floor like mad pythons, constantly tangling with electrical cables for inspection lights and causing workers to trip as they moved between stations. A worker moving from position A to position B had to disconnect their air hose, coil it, navigate around 3 other workers, find a new connection point, reconnect, and resume work. This 30-second process was repeated 70 times on each wing section. And that's not all. There was also the problem of heat. Seattle in January wasn't known for its warmth, but the factory was hot. 17 workers crowded around a single wing section, each generating body heat, each pneumatic gun adding more heat to the confined space. The aluminum sheet absorbed this heat and expanded microscopically. Not by much, just 0.003 inches over a 10-foot section. But when you're trying to align pre-drilled holes with a tolerance of 0.002 inches, this expansion meant the holes didn't match. Reamers spent 15% of their time using tapered reamers to enlarge holes that shrank due to misalignment as the metal cooled. None of this was in the engineering specifications because no one anticipated 17 people working in such close proximity for such extended periods. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, don't forget to tell us in the comments where you're watching this video from. Frank Schmansky didn't look like a man who could change the course of a war. He was 31, 5 feet 7 inches tall, and his hands were perpetually stained with aluminum dust and grease. Before Pearl Harbor, he'd worked at a Chrysler plant in Detroit, installing door panels on Windsor sedans. Repetitive, monotonous work, the kind where your hands knew what to do before your brain caught up. When Boeing started hiring in late 1941, Frank moved his wife and 2 daughters to Seattle, rented a room in a boarding house near the plant, and joined the evening shift at Wing Assembly Station 4. He started at 4 p.m. and finished at midnight, 5 days a week, sometimes 6, when production quotas demanded it. What set Frank apart wasn't his riveting skill. Dozens of workers could match his speed and accuracy. What made him special was that Frank couldn't stop observing the entire process. Most riveters focused on their immediate task: align the gun, pull the trigger, move to the next rivet. Repeat 400 times a shift. Frank, however, saw the whole ballet. He noticed that Jenkins, working on the third row, always waited for Patterson to finish the second row. He noticed that Patterson always waited for quality control to clear the first row. He noticed that the sequence created a cascade of delays that geometrically increased as they progressed across the wing's surface. On February 4th, during his midnight break, Frank sat on an overturned parts crate, eating a sausage sandwich and watching a finished wing section being moved to final assembly. Something about it bothered him. The rivet pattern looked perfect from a structural standpoint. Each row overlapped the previous one, creating that shingle effect the engineers loved. But Frank kept thinking about his old job at Chrysler. When they installed door panels, they didn't start at one edge and work their way across the entire surface. They started at the four corners simultaneously and worked inward. Why? Because it allowed four workers to work in parallel without getting in each other's way. The geometry of the door panel made parallel work possible. He looked again at the wing diagram posted on the station's bulletin board. The rivet pattern ran in straight lines from the leading edge to the trailing edge, parallel rows traversing the wing's surface. But the wing itself wasn't a flat rectangle. It was a complex three-dimensional structure with depth, with internal ribs creating separate chambers with access points in specific locations. What if the rivet sequence matched the wing's actual geometry rather than treating it like a flat sheet? What if they started from several points simultaneously? Points chosen because they provided workers with maximum physical access without overlapping. Frank grabbed a pencil and began sketching on the back of his time card. Instead of straight rows, he drew a pattern that looked almost random. Rivets clustered around structural ribs where access was easiest. Then, diverging lines connected these clusters, following the natural contours of the wing's internal structure. It looked wrong. It looked like someone had scattered rivets across a blueprint and decided to leave them where they fell. But as Frank traced the pattern with his finger, he realized something important. 5 workers could be riveting simultaneously, with none of them requiring the same physical space. Worker 1 could be at the wing root inside the main spar chamber. Worker 2 could be mid-wing accessing through an inspection panel. Worker 3 could work on the trailing edge, which was shallow enough for top-down riveting without bucking. They would never intersect. The structural implications worried him. The engineering blueprint specified that parallel row pattern for a reason: load distribution, stress concentration, terms Frank only half understood. But he kept thinking about something else he'd noticed. Rivet failures almost never occurred where 2 rows met. They happened at transition points, where the wing skin changed thickness, or where cutouts for fuel tanks interrupted the pattern. The rows themselves weren't magic. They were just one way to distribute fasteners across a surface. Perhaps not the only way. Frank knew what would happen if he approached a production supervisor with his sketch. He'd be politely smiled at, told that engineers had spent months calculating those rivet positions, and sent back to his station. The hierarchy at Boeing Plant 2 was rigid. Engineers designed, managers managed, workers assembled. No one expected innovation from a guy whose job title was Riveter Second Class. Imagine doing the same thing for years, following rules that seem unbreakable. And then one day, an idea comes to you that turns everything upside down, an idea that, by all conventions, should be absurd. But it might just be the key to saving not only your project, but an entire industry. What if what you consider a mistake is actually a brilliant solution? How often have you found your intuition telling you one thing, while official instructions demanded another? In this video, we'll tell a story that will make you rethink the very concept of efficiency and strength. A story about how one person's courage challenged decades of engineering dogma and changed the course of history. Are you ready to discover why sometimes the wrongest solutions are the only right ones? At the heart of a grand production, on assembly lines where mighty flying fortresses were born every day, worked Frank, an ordinary riveter second class. Like many, he faced routine and seemingly unshakable rules. But Frank had one undeniable advantage. He worked the night shift, and his supervisor, Bill Hendricks, was an unusual man. Hendricks, who started as a tinsmith before becoming a foreman in 1940, was distinctive in that he genuinely listened to those who toiled on the factory floor. This made him either incredibly progressive or dangerously naive, depending on one's perspective. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription, and of course tell us in the comments where you're watching this video from. Your support helps us create more such stories. On February 11th, Frank managed to catch Hendricks during the 8 p.m. shift and show him his sketch. The supervisor studied it long and carefully, then said something completely unexpected to Frank. "This violates every principle of structural load used by Boeing. You understand that, don't you?" Frank nodded. He at least suspected that was the case. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, tell us in the comments where you're watching this video from. Your support helps us create more such stories. Hendricks continued to explain. The parallel arrangement of rows is not random. When the wing bends under load, stress concentrates along predictable lines. The rivet rows are positioned perpendicular to these stress lines. This is fundamental knowledge laid out in every aerospace engineering textbook published since 1927. The principle Hendricks described was the result of work by Theodore von Karman and his Caltech team in the late 1920s. They mathematically proved that fastener patterns in load-bearing structures must follow stress trajectories, invisible lines of force that permeate the metal under pressure. The B-17 bomber wing, carrying 6,500 pounds of fuel and the structural weight of 4 powerful engines, experienced colossal bending loads during flight. The lower surface was under constant tension, trying to elongate, while the upper surface was subjected to compression. Along the center line, the so-called neutral axis, there was virtually no stress. Von Karman's equations irrefutably demonstrated that fasteners should be densest where stress peaked, and could be spaced more sparsely in areas of minimal stress. The parallel rivet pattern perfectly aligned with this principle, where each row precisely corresponded to a specific stress magnitude, and the spacing between rivets was carefully calculated to meet the necessary load requirements. It seemed like an unshakable truth. But what if even the most perfect theory doesn't account for the full complexity of the real world? Frank's proposed design decisively rejected all these established canons. His rivet clusters concentrated around structural ribs, not along stress trajectories, as science demanded. His radial connections followed principles of worker accessibility, not optimal load distribution paths. From a classical engineering perspective, this was complete nonsense, a kind of engineering absurdity. Perhaps such a wing might endure taxiing tests, or even a few initial flights. However, under prolonged combat stress, microcracks would inevitably appear, where the rivet pattern did not align with stress distribution. These cracks would begin to propagate, and eventually the wing would fail. This would mean unavoidable loss of life. Hendricks patiently explained all these intricacies to Frank right in the middle of the noisy factory floor, shouting over the roar of pneumatic rivet guns. Then he posed a question that fundamentally altered the course of their conversation, and perhaps the future of aviation. But did von Karman ever consider assembly efficiency as a structural factor? Frank looked puzzled, not understanding where his supervisor was going with this. Hendricks continued, revealing his radical idea. If it takes us 20 hours to rivet one wing, and we make mistakes because workers are exhausted, cramped, and constantly bumping into each other, how many of those 12,000 rivets are actually installed to specification? How many are slightly loose because the bucker missed the timing? How many holes are slightly oversized due to imperfect alignment? Your design might be theoretically less strong, but what if it creates practically stronger wings due to perfect installation quality? This was a true challenge to established beliefs, a harbinger of impending conflict. Such reasoning was pure heresy to the established engineering school. Boeing's quality control processes were based on the unwavering assumption that workers meticulously followed procedures. These procedures, in turn, were developed from the strictest engineering specifications. If wings failed quality inspection, the logic dictated that workers should be retrained or fired, and more skilled ones hired. Reworking an aircraft design to accommodate human limitations was considered absolute nonsense. It would be akin to the tail wagging the dog, disrupting the entire hierarchy and common sense. However, in 3 years as a supervisor, Hendricks had noticed something. He realized that theoretical perfection and harsh practical reality diverged far more than engineers were willing to admit. He saw riveters so exhausted by the 18th hour of wing assembly that their hands began to shake. He witnessed buckers missing their timing because they had been in the same cramped position for 40 minutes, their legs cramping. He saw quality inspectors approve slightly loose rivets because a rejection would mean another 2-hour delay, and production quotas already seemed impossible to meet. What if Frank's incredible design, by reducing assembly time and worker fatigue, could actually ensure more reliable and flawless installations? This question hung in the air, portending a storm that could either destroy or save the company. Hendricks carefully folded Frank's sketch and tucked it into his pocket. "I'll talk to someone," he promised. Frank returned to his rivet gun, not expecting anything significant. Hendricks did not approach the chief engineer. Such a move would have been suicidal. Oliver Eccles, head of Boeing's B-17 engineering program, had a reputation for ruthlessly eating alive shop floor supervisors who dared to challenge his designs. Instead, Hendricks went to Donald Douglas, no relation to the aircraft company of the same name, who served as assistant production superintendent. Douglas was only 3 weeks away from being fired if production numbers didn't improve. His desperate situation made him open enough to listen to even the craziest and most unorthodox ideas. This desperation would be the key to a potential breakthrough. On February 18th, Douglas studied Frank's sketch for only about 30 seconds before decisively declaring, "This is garbage. Get it out of my office." But Hendricks didn't budge. Instead, he pulled out his notebook and showed Douglas something entirely different: the wing assembly time logs for Station 4 over the past 6 weeks. Every single wing had required 19 to 22 hours of work. There was not a single exception, not a single crew that had managed to speed up the process. The bottleneck was fundamental, embedded in the very manufacturing process. Like an invisible wall preventing progress, these weren't just numbers, they were a verdict on the existing system. Douglas looked at the numbers again, then back at the sketch. Even if it works for efficiency, Eccles will never approve this. Never. He'd rather shut down the plant than allow a non-standard riveting pattern on a wing, he said, clearly aware of the scale of resistance. And here lay a truth Douglas understood far more deeply than Hendricks. Boeing was mere weeks away from completely losing its B-17 production contract. Consolidated Aircraft was actively lobbying the Army Air Forces, arguing that their B-24 Liberator was significantly easier to manufacture and could be produced in much greater quantities. General Arnold was listening intently to these arguments. If Boeing couldn't demonstrate substantial production improvements by March 15th, the Army would divert orders to Consolidated and other manufacturers. Boeing might retain some production, but would lose its dominant position as America's primary heavy bomber supplier. This would mean massive layoffs. It would mean the collapse of Seattle's economy. And, no less importantly for Douglas, it would mean he would lose his job anyway. In this desperate situation, even the wrongest solution might be the only salvation. Douglas, on the verge of being fired, made a decision that contravened 17 different Boeing company protocols. He authorized a test without engineering department approval. However, conducting this during the day shift, with senior management walking the factory floors, was impossible. The evening shift was also unsuitable due to the large number of witnesses. So he scheduled the test for the night shift, February 21st, starting at midnight. He took a wing section already rejected by quality control for unrelated reasons. A damaged spar made it unfit for flight. This way, in case of catastrophic test failure, they wouldn't waste a good wing. He enlisted Frank and 4 other riveters, seasoned veterans of the evening shift who volunteered, and he told absolutely no one. The test began at 0014. Frank had spent 3 days refining his design, precisely determining which rivet clusters went where, calculating sequences that would allow all 5 workers to operate simultaneously. He color-coded the blueprint: red for the first worker, blue for the second, green for the third, yellow for the fourth, purple for the fifth. Each color denoted a physical zone that did not overlap with other color zones. Workers could literally rivet simultaneously, without coordinating actions, without waiting, without bumping into each other. It was madness to watch. Traditional riveting had a rhythm, a sequential logic. This looked like controlled chaos. One worker was inside the main spar cavity. Another was under the trailing edge. A third worked from above, near the leading edge. They didn't follow rows. They followed clusters. And these clusters seemed haphazardly scattered. Douglas stood 30 feet away with a stopwatch, chain-smoking Lucky Strike cigarettes. Hendricks stood beside him, silent. Every 15 minutes, Douglas checked the time and recorded it. At the 2-hour mark, the wing should have been approximately 20% complete. It was 45% done. The workers began to realize something unusual was happening. They weren't waiting, not for each other, not for inspectors, not for access. Every rivet position Frank had marked was indeed accessible without interference. Pneumatic hoses didn't tangle because workers didn't cross paths. Heat buildup was lower because they weren't crowded in one area. The aluminum didn't expand as much because 5 heat sources distributed across the wing's surface created a less concentrated thermal load than 17 sources in one spot. At 02:21, 127 minutes after starting, the last rivet was installed. Douglas clicked the stopwatch. He said nothing. He walked to the wing and began selectively inspecting rivets, pulling out a bore scope to check the proper formation of the bucktail. Chris held his breath. Frank stood, covered in aluminum dust, trying to read Douglas's expression. Douglas inspected 30 rivets before he believed his eyes. Every single one was perfect. The bucktails were uniform, properly seated, with no gaps between the aluminum sheets. He called Jimmy Chen, the night shift quality inspector, without explaining what he was inspecting. Chen grabbed his toolkit and began a full inspection protocol, the same one he had performed on 200 previous wings. He checked rivet spacing with calipers. He used a thickness gauge to check sheet metal compression. He tapped each rivet head with a small ball-peen hammer, listening for the dull thud that indicated proper seating as opposed to the hollow clang of a loose rivet. 40 minutes later, Chen looked up and said, "It passes. I don't know which crew did this, but the work is clean." Douglas told him how long it had taken. Chen thought he was joking. Then he decided the stopwatch must be broken. Then he rechecked his inspection. Because wings riveted. That quickly shouldn't be that clean. There should have been mistakes, haste, something wrong. He found nothing. The wing was perfect. Even better than perfect, in fact. Chen had been inspecting B-17 wings since July 1941 and kept a personal defect log he never showed management. On average, each wing had 140 rivets requiring attention during quality control. Loose rivets, misaligned holes, installation errors. This wing had $11 less than 1/10 of the usual defect rate. However, passing a visual inspection did not guarantee the wing would withstand flight loads. The riveting pattern was still completely wrong from a structural engineering perspective. Douglas knew they needed real tests, requiring equipment and authorization he didn't have. At 3:30 a.m., he made another unauthorized decision. He called the night crew at the test station in Building 7 and ordered them to prepare for an emergency load test. He didn't mention that the wing used an unapproved riveting pattern. He simply said they needed urgent testing of a wing section for production validation purposes. The test center had equipment designed to simulate flight loads. A massive hydraulic press could apply up to 150,000 pounds of force to a wing section, bending it up and down to replicate in-flight maneuver stress. Standard B-17 qualification required wings to withstand loads equivalent to 6, 2 times the aircraft's maximum weight without residual deformation. This was the safety margin. U.S. Army Air Force's specification R-1816B, established in March 1941, mandated these tests for any structural modification to production aircraft. Douglas was about to test a wing that violated R-1816B in every possible way, using a facility not authorized for non-standard tests. At 4 a.m., with no one watching, they mounted the wing section into the test rig. At 4:15 a.m., the hydraulic press engaged, applying upward pressure that bent the wing tip upward. Douglas watched the strain gauges. At a load equivalent to 1G, the wing flexed normally. At 3G, still normal. At 6G, the deflection precisely matched specifications. At 2G, the qualification threshold, the wing held. No creaks, no popping rivets, no crack formation in the aluminum skin. Douglas told the operator to continue. At 7G, the wing was still structurally sound. At 8G, individual rivets near the wing root began to show deformation, but this was expected. The wing root bore the highest loads and was designed to be the first point of failure. At 4G, the test was stopped not because the wing failed, but because Douglas was terrified of breaking the test equipment. Have you ever felt like you're on the verge of something monumental, but invisible walls of rules and fear hold you back? What if the only path to a breakthrough lies in breaking every imaginable convention? Today we're not just telling a story about building airplanes, but about a man who dared to challenge the system when the stakes were higher than the sky. How did he pull it off? And what can his experience tell us today about our own seemingly impossible situations? In a world where every step is regulated and deviation from the norm is considered a disaster, there was an engineer whose name might have been forgotten were it not for his incredible audacity. He stood on the edge of a precipice, his career hanging by a thread, facing a task no one could solve. But instead of giving up or following meaningless directives, he did what no one dared. He violated some 17 different Boeing protocols. He authorized testing without engineering department approval, knowing it could cost him everything. In this video, we'll reveal how one man, risking it all, not only solved a critical production problem, but also radically improved a process that was considered perfect. And the first lesson he taught us begins right now. Stay with us and watch until the end, because this story is full of unexpected twists. We'd be especially grateful for a like and a subscription. And of course, let us know in the comments where you're watching from. But how do you pull off something like this under the strictest control? During the day, with senior company management walking the factory floors, it was unthinkable. The evening shift wasn't suitable either. Too many eyes might notice. So, Douglas scheduled the test for the dead of night, February 21st, exactly at midnight. He chose a wing section that had already been rejected for other reasons. A damaged spar made it unfit for flight. This was his insurance policy. If the experiment went catastrophically wrong, they wouldn't lose a valuable, usable wing. And for this secret mission, he enlisted only Frank and 4 other riveters, proven veterans of the evening shift who volunteered to help. No one else knew about what was coming. So the test began at 0014. Frank, the protagonist of this daring experiment, had spent 3 full days meticulously refining his unique scheme. He precisely calculated to the millimeter which groups of rivets should go where, and he designed a sequence of actions that would allow all 5 workers to work simultaneously without getting in each other's way. To avoid confusion, he even color-coded the blueprint. Red for the first worker, blue for the second, green for the third, yellow for the fourth, purple for the fifth. Each color designated a separate physical zone that did not overlap with the others. This meant the riveters could literally work in sync without needing to coordinate their movements, without pauses, and without collisions. From the outside, it looked absolutely wild. While traditional riveting had a clear rhythm and logical sequence, this resembled controlled chaos. One worker was inside the main spar cavity, another under the trailing edge, a third on top, near the leading edge. They didn't follow rows. They worked by clusters that seemed completely randomly scattered. Douglas stood 10 meters away, tense, chain-smoking, lucky strikes, and glancing at his stopwatch. Hendricks, his colleague, stood beside him, maintaining complete silence. Every 15 minutes, Douglas checked the time and made notes. 2 hours after the start, under normal conditions, the wing would have been about 20% complete, but now, to everyone's astonishment, it was already 45% finished. The workers themselves began to realize something extraordinary was happening. They weren't losing a single second, not waiting for each other, not for inspectors, not for access to the necessary sections. Every rivet point, carefully marked by Frank, was absolutely accessible without any obstruction. The pneumatic hoses, which usually constantly tangled, remained untangled because the workers didn't cross paths in their movements. Heat buildup was also significantly lower. Instead of crowding into one area, they were evenly distributed across the surface. As a result, the aluminum didn't expand as much because 5 heat sources distributed across the entire wing area created a much less concentrated thermal load than 17 sources concentrated in one place. Finally, at AO2.21, 127 minutes after the start, the last rivet was installed. Douglas clicked the stopwatch. He didn't utter a word. He slowly approached the wing and began selectively inspecting rivets, pulling out his borescope to ensure the proper formation of the bucktail. Chris, one of the workers, held his breath. Frank, covered in aluminum dust, stood nearby, trying to read anything from Douglas's expression. Only after Douglas had checked 30 rivets did he finally believe his own eyes. Every single one was impeccable. The bucktails were perfectly uniform, correctly seated, with not the slightest gaps between the aluminum sheets. Then Douglas called Jimmy Chen, the night shift quality inspector, without going into detail about what he was inspecting. Chen, without asking questions, grabbed his toolkit and began the full inspection protocol, the very same one he had already performed on 200 previous wings. He meticulously measured the distance between rivets with calipers. Using a thickness gauge, he checked the degree of sheet metal compression. He tapped each rivet head with a small ball-peen hammer, carefully listening for the dull, confident thud that indicated proper seating, in contrast to the hollow clang of a loose rivet. 40 minutes later, Chen looked up and declared, "It passes. I don't know which crew did this, but the work is flawless." Douglas told him how long the job had taken. Chen initially thought Douglas was joking. Then he decided the stopwatch must be broken. After that, he meticulously rechecked his inspection, because wings riveted at such an incredible speed simply couldn't be that clean. There should have been mistakes, signs of haste. Something was bound to go wrong. But he found nothing. The wing was perfect. In fact, it was even better than perfect. Jimmy Chen had been inspecting B-17 wings since July 1941, maintaining a personal, highly confidential log of defects that he never showed to management. According to his records, an average wing typically showed about 140 rivets, requiring attention during quality control, which could include loose rivets, misaligned holes, or installation errors. This particular wing, however, had only 11 less than a tenth of the usual defect rate. It was simply unheard of. However, passing a visual inspection did not guarantee the wing would withstand the colossal stresses of actual flight. The riveting pattern, despite its flawless execution, was still considered structurally unsound from an engineering perspective. Douglas knew they needed real serious tests, the kind that required specialized equipment and official authorization, neither of which he possessed. So, at 3:30 a.m., he made another unauthorized decision. He contacted the night crew at the test center in Building 7 and ordered them to prepare for an emergency stress test. He, of course, omitted the detail that the wing used an unapproved riveting pattern. He simply stated that an urgent wing section test was needed to verify manufacturing parameters. What would happen when this wing faced unimaginable loads? The test center was equipped with advanced machinery specifically designed to simulate flight loads. A powerful hydraulic press could apply up to 150,000 pounds of force to a wing section, bending it up and down to precisely replicate the stresses encountered during aerial maneuvers. Standard qualification for B-17 bombers required wings to withstand loads equivalent to 2 times the aircraft's maximum weight without any residual deformation. This was a critically important safety margin. U.S. Army Air Force's specification R-18-6B, approved in March 1941, mandated such tests for any structural changes in production aircraft, and Douglas was about to test a wing that violated this R-18-16B specification in virtually every possible way, using a facility that was not officially authorized for non-standard tests. The tension mounted. At 4 a.m., under the cover of night, unseen by anyone, the wing section was mounted into the test frame. At 4:15 a.m., the hydraulic press engaged, slowly applying upward pressure that bent the wingtip skyward. Douglas kept his eyes glued to the strain gauges. At a 1G load, the wing flexed perfectly normally. At 3G, still no deviations. At 6G, the deformation precisely matched the specified requirements. And then at 2G, the qualification threshold, the wing held. No creaks, no popping rivets, no hint of cracks in the aluminum skin. Douglas, gripped by a mix of astonishment and hope, ordered the operator to continue. At 7G, the wing remained structurally sound. At 8G, individual rivets near the wing root began to show signs of stress. But this was entirely expected. The root bore the maximum loads and was designed to be the first point of failure. At 4G, the test was stopped. Not because the wing failed, but because Douglas was terrified he would break the test equipment itself. Do you ever feel like you're meticulously following all instructions, yet still hitting insurmountable obstacles? What if all your experience, all your usual approaches, are actually leading you down the wrong path? Today, we're going to uncover an astonishing story that will make you rethink the fundamental principles upon which success is built. Prepare to learn how one seemingly minor change, arising against all established norms, didn't just solve a critical problem, but fundamentally altered the course of an entire war and forever rewrote the rules of manufacturing. Imagine this scene. Engineers, holding their breath, watch the test equipment. The hydraulic pressure is gradually released from the aircraft wing, which had just been subjected to incredible loads. According to all calculations, after such a test, simulating an 4G overload, the wing should have shown at least some residual deformation, a microscopic but inevitable trace of stress. That's how all structures built to standard blueprints are supposed to work. But what they saw defied everything they knew. The wing returned to its original position completely intact, with no sign of deformation. 0. As if it had withstood a load of no more than 5G. Engineer Chen, responsible for the inspection, reviewed the protocol again and again, checking every rivet that had been under maximum pressure. Not one had loosened. Not one showed signs of microscopic displacement. This wing was inexplicably stronger than all its predecessors. Stay with us and watch this video to the end, because the further developments will amaze you with their unpredictability. We would be especially grateful for your like and subscription, and if you write in the comments where you're watching us from. It will be an additional motivation for us to create even more engaging content. At that moment, at 5:47 a.m., Engineer Douglas stood trying to comprehend what he had witnessed. He knew that at the heart of this phenomenon was Frank's riveting pattern, which seemed random, almost chaotic. But in reality, it was a stroke of accidental genius. Frank had placed groups of rivets around the structural ribs, which are known to be the primary load-bearing elements. By concentrating fasteners precisely where the structure was strongest, Frank inadvertently created a pattern that didn't fight the natural load distribution paths in the wing, but rather reinforced them. The radiating connections between clusters acted as secondary stress distributors, diverting loads away from potentially weak points. This wasn't a chaotic arrangement. It was an organic system that mimicked the actual flow of forces in the structure, not how engineers were accustomed to thinking they should flow. By 6:00 a.m. on February 21st, Douglas realized that this incredible discovery needed to be immediately brought to someone who could authorize its full-scale implementation. He understood that Eccles would likely kill the initiative on principle. So, Douglas drove directly to the home of James Murray, Boeing's vice president of manufacturing operations, waking him at his Laurelhurst residence. Murray arrived at the plant at 7:15 a.m., still in his weekend casual clothes, and demanded all the data, test results, inspection reports, time logs. He watched carefully as Douglas's hands trembled while explaining what they had done without official authorization. Murray's face remained impassive. Then he asked the only question that truly mattered. Can we train 200 riveters to use this pattern by Monday? Douglas hadn't thought that far ahead. He was so consumed with proving the concept worked that he hadn't considered scaling. Murray was already running the numbers in his head. If one wing now took 2 hours instead of 20, and Boeing had 42 wing assembly stations, that meant they could increase wing production tenfold without hiring a single additional worker. Wings were the bottleneck. Fuselages were being assembled faster than they could be joined to wings. Tail sections were piling up, waiting for completed aircraft. The entire production line was limited by the speed of wing assembly. Remove that bottleneck, and everything else would start moving. That morning, Murray made a fateful decision, despite Eccles's furious objections, protests from the engineering department, and grim warnings from Boeing's legal team about potential liability if the wings failed in combat. Murray ordered the new riveting pattern implemented on all production lines, starting February 25th, 1942. He gave Frank Szymanski a $40 a week raise and the title Production Methods Specialist. Chris received a promotion to senior supervisor. Douglas was told his job was safe, and Murray made it clear to Eccles if he didn't like it, he could personally explain to General Arnold why Boeing was still only producing 14 bombers a month. The results were staggering. In March 1942, Boeing's Seattle plant delivered 47 B-17 bombers. In April 91. By June, they reached 186 aircraft, but the real breakthrough came in July, when all 42 wing assembly stations were fully converted to Frank's pattern, and workers had perfected the new sequence. Production in July: 284 B-17s. August 319, September 362 bombers rolled off the assembly line in a single month. This exceeded the entire annual production of 1941. The impact on the air war was immediate and catastrophic for the Luftwaffe. In October 1942, the 8th Air Force flew its first mission involving over 100 bombers to strike industrial targets in Lille, France. The Luftwaffe was designed for defensive combat against raids of 20 or 30 bombers. They could encircle such formations, pick off stragglers, making each mission costly enough to be unprofitable. But 100 bombers, the defensive fire from that many B-17s, created overlapping kill zones, making fighter attacks suicidal. German pilots called it the wall of lead. They lost 3 fighters to shoot down 1 bomber, and the Americans kept coming. By January 1943, the 8th Air Force was flying missions with 300 bombers. By summer, with 500. Each of these planes represented 2 hours of riveting instead of 20. Each delivered 4,000 pounds of bombs deeper into Germany than Hitler thought possible. The Schweinfurt-Regensburg missions in August 1943, raids that crippled Germany's ball-bearing production, required 376 B-17s. Without Frank's pattern, Boeing would not have built that many bombers by August 1943. The entire strategic bombing campaign, an effort that diverted German fighters from the Eastern Front and forced the Luftwaffe into an unsustainable war of attrition, depended on Boeing's ability to flood the skies with flying fortresses. Boeing's Seattle plant wasn't the only facility using Frank's pattern. By April 1943, Boeing's Wichita plants, Douglas in Long Beach and Lockheed Vega, had adopted various versions of the scheme. Total production across all facilities reached 512 heavy bombers in a single month. The Germans were producing 1,000 fighters monthly to counter them, but it didn't matter. You can't win an air war when the enemy builds bombers faster than you can shoot them down. Frank Szymanski never became famous. In July 1943, he received an appreciation from the War Production Board, a certificate signed by a man he'd never met. This document hung in his daughter's bedroom until she moved out in 1959. Boeing gave him a raise and a fancy title. But after the war ended, production methods specialist positions were quietly eliminated during the 1946 layoffs. Frank returned to Detroit, worked at a Ford plant for 23 years, and died in 1971, never knowing that his riveting pattern fundamentally changed aircraft manufacturing methods. For it truly did change everything, though not immediately, and not obviously. But the principle Frank stumbled upon became doctrine. In 1947, when Boeing began designing the B-47 Stratojet, its first swept-wing jet bomber, engineers didn't start with theoretical riveting patterns. They started by consulting with assembly line workers about access points and workflow organization. The B-47 wing used a pattern that looked chaotic on paper, but could be riveted by 6 workers simultaneously in 3 hours. Have you ever felt that your experience, your hands-on knowledge, your deep understanding of a craft is actually more valuable than any theory? But no one listens to you. Many of us face situations where academic knowledge is lauded, while true wisdom, born from thousands of hours of work, goes unnoticed. However, there are stories that prove the opposite. Stories of how a simple person changed an entire industry, overturning conventional ideas about what constitutes ideal design. Today, we're going to uncover a paradox that once revolutionized aircraft manufacturing: how world-class engineers overlooked the most obvious truth for decades. until a man without a college degree showed it to them. You probably make this mistake every day without realizing it, favoring complex schemes over simple yet effective solutions. Forget everything you've been taught about ideal design. It's a lie if it doesn't account for the reality of execution. By the way, if you want to learn how practical experience can change the world, stay with us and watch this video to the end. We'd be especially grateful for your like and subscription. And please write in the comments where you're watching us from. We're very interested to know our audience. No one called it the Szymanski method back then. No one even knew a Szymanski existed. People simply knew that aligning riveting patterns with actual assembly conditions rather than pure structural theory resulted in better planes built faster. Douglas Aircraft applied this same principle when developing the DC-8 in the late 1950s. Lockheed used it for its legendary C-130 Hercules. When Boeing engineers designed the 707, their first commercial jetliner, assembly line supervisors were included in their initial design review team. This was a truly revolutionary concept, asking the people who would actually build the product if the proposed design could even be manufactured. The 777's fuselage panels used what Boeing internally called cluster riveting, essentially Frank's pattern, but now with a corporate name. This reduced the 707's fuselage assembly time by 60% compared to the Stratocruiser it replaced. If this story is already making you ponder the value of practical experience, stay with us and watch until the end. We'd be especially grateful for your like and subscription. And of course, write in the comments where you're watching us from. It's very important to us. The true legacy of this idea manifested in the modern philosophy of aerospace manufacturing. There's a principle called design for manufacturability, or DFM, which every aerospace engineer studies in university. Today, it asserts that the elegance of a design is measured not only by its performance, but also by how efficiently it can be built. The textbook example taught at MIT Caltech and every aerospace engineering program worldwide is the B-17 wing riveting. How a theoretically optimal pattern proved worse than a practically optimal one, how reducing assembly time improved quality rather than diminishing it. Most students will never learn about Frank. They study Boeing's innovative manufacturing methodology development program as if it were a committee decision. Modern aircraft, like the Boeing 787, take this idea even further. The 787's fuselage sections are joined using computerized fastening patterns that appear random, but are optimized for robotic installation. Each pattern is generated by algorithms that simultaneously consider structural loads, assembly access, thermal expansion, and about 20 other variables. Frank did the same thing in 1942 with a pencil and a time card. He just didn't have the math to prove why it worked. He had something better. He had pattern recognition developed from observing thousands of rivets installed and noticing what slowed everyone down. And that's the uncomfortable truth this story reveals. Frank wasn't smarter than Boeing's engineers. He didn't have a better education. He didn't understand von Karman's stress equations or load path analysis. He had different knowledge. He knew how tired you get sitting in the same position for 40 minutes. He knew how pneumatic hoses get tangled when workers cross paths. He knew that theoretical perfection, executed poorly, yields worse results than theoretical imperfection, executed flawlessly. Boeing engineers knew how to calculate stresses. Frank knew how to actually build things. Both types of knowledge were necessary. But only one type was valued. The aerospace industry eventually learned this, but it took decades. Modern aircraft development uses integrated product teams, where machinists and assemblers work alongside engineers from day one. When Airbus designed the A380, the largest passenger aircraft ever built, assembly line workers had veto power over design decisions that would make production impossible. This is Frank's true legacy, not the specific riveting pattern, which is now obsolete in the age of automated fastening systems. The legacy is the idea that the person doing the work can understand the work better than the person who designed it. Revolutionary in 1942. Common sense now. Except that we constantly forget it and have to relearn. Every innovation cycle produces its own Frank Szymanski, the person who sees the obvious solution that experts are too educated to notice. Smart organizations listen. The rest continue riveting wings for 20 hours and wonder why they're losing.